Welcome to our very first lecture on non-chordates. Today, we're going to explore the fascinating world of helminths, or parasitic worms. We will discover how these incredible creatures have evolved to survive in one of the most hostile environments imaginable, the inside of another living animal. By the end of this video, you will understand not just what these adaptations are, but the beautiful mathematics behind why they work. To truly appreciate these worms, imagine you are a tiny stowaway trapped inside a giant, active chemical factory. This factory is filled with acid baths, crushing mechanical forces, and roaming security guards, the host's immune system, constantly trying to eliminate you. To survive, you would need grappling hooks to hold on, a protective suit to resist the acid, and a way to steal energy unnoticed. In the biological world, helminths face this exact terrifying scenario, and they have developed incredible body modifications to hide and thrive. Now that we understand the hostile environment they face, let us look at how they actually survive it. In zoology, parasitic adaptations are the profound changes helminths have evolved over millions of years. These fall into three categories. Morphologically, they lose unnecessary organs like eyes and develop powerful attachment tools like hooks and suckers. Physiologically, they secrete anti-enzymes to neutralize stomach acids and switch to breathing without oxygen. Finally, reproductively, they dedicate almost their entire body to producing millions of eggs to ensure at least a few survive. These adaptations are not just fascinating biological trivia, they are a critical matter of global health. Millions of people and animals suffer from diseases caused by these worms, leading to severe malnutrition and massive economic losses in agriculture. By studying how these parasites attach to the intestine, scientists can develop targeted drugs that paralyze their hooks, flushing them out harmlessly. Understanding their protective outer layer, called the tegument, helps researchers design medicines that strip away this armor, allowing the host's immune system to finally destroy the invader. Understanding how we fight them brings us to one of their most extreme adaptations. Tapeworms have completely lost their digestive system. Because they live in an intestine where the host has already digested the food, they simply absorb nutrients directly through their skin. But to do this efficiently, they need a very specific physical shape. They must expose a massive surface area to the nutrient-rich fluids around them, while keeping their internal volume as small as possible. This is why tapeworms are incredibly flat and ribbon-like. This need to be flat brings us to the mathematics of survival. The efficiency of absorbing food through the skin is governed by the surface area to volume ratio. In this formula, RSAV represents that ratio. A stands for the total surface area of the worm exposed to the host, measured in square millimeters. V represents the total internal volume of the worm in cubic millimeters. This tells us that absorption efficiency is directly proportional to surface area. If the surface area increases while the volume remains small, the parasite can absorb food rapidly. Now that we have our formula, let us see this with a concrete example. Imagine a hypothetical flat tapeworm that has an internal volume of 8 cubic millimeters. Its dimensions are a length of 4 millimeters, a width of 2 millimeters, and a height of 1 millimeter. To find its surface area, we use the standard geometric formula for a rectangular prism. We plug in our length, width, and height. Multiplying these out gives us 8 plus 2 plus 4 inside the parentheses, which is 14. Multiplying by 2 gives us a final surface area of 28 square millimeters. So, we have calculated the surface area, but how does this prove the flat shape is better? Let us compare it to a cube-shaped worm with the exact same volume of 8 cubic millimeters. First, we divide our flatworm's surface area of 28 by its volume of 8, giving a ratio of 3.5. Now, a cube with a volume of 8 has sides of 2 millimeters. Its surface area would be 6 times 2 squared, which is 24. Dividing 24 by 8 gives a ratio of exactly 3. Because 3.5 is greater than 3, the mathematics clearly proves that the flat shape is a superior evolutionary adaptation. This mathematical advantage in feeding is incredible, but feeding is only half the battle. The other major adaptation is hyperreproduction. A parasite's life cycle is incredibly dangerous. When a parasite lays eggs, those eggs must leave the host, survive in the harsh outside environment, and somehow be swallowed by a completely new host. The chances of a single egg successfully making this journey are astronomically low, often less than 1 in a million. To overcome this massive statistical disadvantage, helminths have evolved to dedicate almost their entire internal anatomy to producing an unbelievable number of eggs. To truly grasp this challenge, we can model their survival strategy using a simple probability equation. N success represents the final number of offspring that successfully infect a new host and grow into adult worms. E stands for the total number of eggs produced by the adult female parasite. Finally, P survive represents the probability that any single egg will survive the environmental hazards. In plain English, the number of successful offspring is just a fraction of the total eggs laid. Because the survival probability is extremely close to 0, the parasite must drastically increase the egg count. Let us apply this formula to a real-world monster, the human roundworm, Ascaris lumbricoides. A single female Ascaris is an absolute egg-laying machine, capable of producing around 200,000 eggs every single day. We want to calculate how many eggs she produces over a full year. We take the daily egg production rate of 200,000 and multiply it by the 365 days in a standard year. This multiplication yields a staggering total of 73 million eggs produced by just one female in a single year. Now that we have this massive number of eggs, let us see why it is absolutely necessary. We take our total egg count of 73 million and apply our survival probability. Assuming harsh environmental conditions, the odds of an egg finding a new host are only 1 in 10 million, which is a probability of 0.0000001. Multiplying these together gives exactly 7.3 successful offspring. This mathematically proves that despite laying over 73 million eggs, only about 7 will survive. If they laid only a few hundred eggs, their species would go extinct almost immediately. To bring all these concepts together, let us look at this diagram of a tapeworm. At the very top, you can see the specialized head region. Notice the sharp hooks at the apex and the muscular, circular suckers on the sides. These are the morphological adaptations that allow it to anchor securely against the crushing forces of the host's digestive tract. Moving down, you see the long, ribbon-like body made of flat segments called proglottids. This flattened shape maximizes the surface area for nutrient absorption. while each of these segments is essentially a massive factory dedicated to producing those millions of eggs we just calculated. We have covered a lot of ground today, so let us summarize the key takeaways. First, helminths are master survivalists that have discarded unnecessary features like eyes, replacing them with powerful hooks, suckers, and protective cuticles. Second, physiologically, they have mastered neutralizing host enzymes and surviving without oxygen. Third, as our mathematical models proved, their flattened bodies perfectly maximize nutrient absorption. And finally, their massive egg production is a calculated strategy to guarantee survival against impossible odds. You now have a deep foundational grasp of how parasites successfully navigate the complex game of life.